Question 17. A group of students are conducting this experiment to work out absolute zero heating or cooling fixed mass of gas. First question, explain and describe how the students can make accurate measurements for the temperature. Well, 1 mark for saying use a thermometer. You could use a digital one or any other thermometer, any temperature sensing gauge. But how would you make it accurate? The 2nd mark is for stirring. Okay, so there's an even temperature, or you could look at the thermometer straight on to avoid parallax, but stirring would be by far the best answer. 2 easy marks. Part B shows a pressure gauge. Why is it sensible to use the PSI scale inside here rather than the Pascal scale on the outside? Okay, you cannot say more accurate or even precise. Okay, there's a smaller spacing between the divisions, which is one way of answering it. So smaller spacing between divisions, or the other way of saying it is, of course, i.e. a higher resolution. You can say either. High resolution is probably the best, but the point is that means there's a smaller spacing. B, part 2. They make a reading of 37 psi. Complete the table, but you need to change the value to kilopascals. Make sure you spot the kilopascals. So fairly easy, I hope. We've got 37 psi. Well, 1 pound is 4.4 newtons, so we're going to multiply by 4.448 newtons. Then we've got it per square inch, so we're going to have to divide by inches, which is 0.0254. That's inches squared per square inch, and if you do that, that gives you the answer 255,000 pascals, so that's 255 kilopascals. So slap that into the table, 255 plus or minus 3. Right, part C. It shows a graph of pressure against temperature. Plot the missing point in, so we have to go 255, and the temperature was 44, so if I go line up at 44, oh, at 255, there you go, there's my point, and draw error bars similar length to what we've got already. Okay, now if you draw your line of best fit, you've not asked for it this time, but error bars should all fit inside your line of best, or be outside your line of best fit. So, part 2, however, is describe what is meant by absolute zero. Make sure you do describe what absolute zero is, and use figure 17.3, that's the graph, to calculate absolute zero. Determine the value, assume the gas behaves as an ideal gas. So a couple of things to do here. 1, explain what is meant by absolute zero, or what do I mean by absolute zero? Really, points here are it's the minimum, or if you like, zero kinetic energy. At absolute zero, the pressure is going to be equal to 0. There's a minimum internal energy. Remember, that's the sum of the random kinetic and potential energies. And what is absolute zero? Well, it's about minus 273. Absolute zero is about minus 273 degrees C. Notice in this question they are using degrees C, not Kelvin, so you don't need to change it to Kelvin. We're in degrees C. How would you plot a graph? How would you calculate absolute zero? Well, if you have a graph of pressure against temperature, and the point where the pressure equals zero, that's your absolute zero. In other words, okay, if we determine the gradient of the line and the crossing point, then we can stick it into the equation y equals mx plus c. When y equals 0, that's this point here, okay, the value of x, or if you like, in this case, x is the temperature, y is the pressure. So when the pressure, y value is 0, the x value, the temperature, is absolute 0. So can I work out the value? Well, from the graph, if you work out the gradient, m, that's going to be equal to, I think I worked it out as 276 minus 220 over 70. That comes out as 0.8. The y-intercept, again, if you look on this graph here, I would say the y-intercept is somewhere around 220. So 220. You stick this into the equation, y equals mx plus c. Y is going to be equal to 0, so pressure is equal to 0. So y is equal to gradient 0.8 times the temperature, x, plus crossing point, y-intercept 220. Rearrange that, minus 220 divided by 0.8 is going to be equal to the temperature, and if you throw that in, that gives you a value of about 275. Now, if you've got the gradient or the intercept slightly different, there's a sort of tolerance here, and the tolerance would be anywhere from between minus 320 to minus 240. As you can see, my value is pretty close to the actual value.